Hi all. In this tutorial, we will introduce you to one of the very interesting data structure topic, that is tree. So far, in the data structure and algorithm series, we talked about linear data structure like arrays, linked list, stack and queues. All of these are linear data structure. In other hand, tree is a non-linear data structure which we are going to cover as a part of this tutorial series. So let's get started with the introduction of tree. A tree is a non-linear data structure as we discussed already. So it consists of nodes and connected by edges, which is used to represent the data in hierarchical form. I know it's little difficult to understand just by the definition. So let me show you the pictorial representation of tree along with example. So this is a graphical representation of a tree. Now let's discuss more about it with the help of example. This example is specific to the employee relationship in the organization, how they are framing a tree of employees in the organization. Let's discuss that. So as you can see on the top of this tree, we have chairman, which is acting as a root node, root or parent of this tree. Now we will be talking in terms of tree by using this organization chart, right? So here, this chairman is having one child, which is CEO. So the CEO is directly reporting to this chairman. Same case, CEO is having one child, which is general manager. So this general manager is directly uh, reporting to CEO, or it is directly pointing to its parent, that is CEO. So if you can see this, GM is indirectly pointing to chairman, which is the root node of this tree, right? So general manager is having its own child. Those are operational manager, financial, marketing, accounting, IT, and HR manager, right? So these all managers are directly reporting to uh, general manager, right? And these all managers are siblings to each other because these all managers in this level are pointing to the same parent. So if you see, this is one of the another tree, or like in the subtree, because this parent is creating one tree inside it because this parent is having its own child. Likewise, uh, if we take this HR manager, right? So HR manager is acting as a parent node here because this HR is having its own childs. See, this is the reference left hand side, right hand side, and this is nothing but a another reference, which is center of the node. Now, each of this node, if you look into this, each of the employees having some names, or in terms of tree, we are considering it as node, right? So each of this node is having some information. This is nothing but a data of or a key of this node. So how this node is creating? This is node. One will be reference, one will be key, another one will be reference, right? So in terms of normal tree, it can be multiple reference. So here you can see we have here one reference, which is chairman to CEO and CEO to general manager. So general manager is having multiple reference. One is operational manager, financial, marketing, accounting, IT, and HR manager. So it has six reference, means six childs. So in normal tree you can have multiple childs, but when it comes to your balance tree, it can be one or two. It can't be more than that. We will discuss that terminology in the later coming up videos. So in this, see here, this is a sales team, let's say, and these are the childs. These are the leaf nodes. Leaf nodes. Not even that, these are also leaves node because there is no any further reference or further child of these nodes, right? These are single nodes, right? So there is no any further childs of these nodes. That's why they are acting as a leaf node, and these nodes are pointing to its parent, so they are also framing a subtree in the main tree. See this. All right. So I hope this will help you to understand about how the relationship is framing in the tree, how tree is basically built. Now let's discuss the component of binary tree. So as you can see in the right hand side, these all are component of tree. So the first component we have is node. So node is an entity that consists key and it's pointed to its child node. So this is a root node and these are the child nodes. So what these nodes are containing, the first thing is key to know the identification of a particular node. The second one is pointer to its child node, right? So if you talk about the first or root node, so this is containing a key which has value a, and the second thing is the pointer to its child node. This is first pointer which is pointing to its left node, and this is second pointer which is pointing to its uh, right node. Now the second one is depth. So depth is a total number of edges from the root node to its target node is called as depth. Means let's say when we want to know the depth of node E, so we want to traverse from the root node to the E, we need to count the number of edges. This is first and this is second. So the depth of node E is 2. And if you want to know the depth of F, so again we need to traverse from the root node to target node, which is F. So we need to count the number of edges from root to target node. So this is first, second, and third. So the depth of F is 3, right? Now the next component we have edges. So connection links of any two nodes are known as edges. So as we have node A and node B, so these nodes are connected with the help of one reference link is known as edges. The next component is root. The first or topmost node of a tree is called as root or parent node. So as we have this top node, which we can call as root node or parent node. But in tree, we can have multiple parent node, but we can have only one root node. Now, the next component we have leaf node. So the node which doesn't have any child is called as leaf node. So let's take example of node B, which is having two child D and E. So we can't call this B node as a leaf node because it is having its child. Now let's talk about D. D doesn't have any further childs, so we can call this as leaf node. So likewise, we have node F, G, H, and C. These node doesn't have its own child, so these nodes are known as leaf node. Now, moving ahead to the next component, that is siblings. So two nodes are said to be siblings if they are represented at the same level and their parents are same. So let's create a label first. This is L1, this is L2, this is L3, and this is L4, right? Now let's talk about D and E. So D and E nodes are in the same level, that is L3. So the first property is true, and the second one is both nodes should be pointing to the same parent. So yes, D and E, both nodes are pointing to the parent B. So it means these both are siblings, right? Now let's talk about another nodes D and F. So D is present in the level 3 and F is present in the level 4. So here the first properties fail that both nodes are present at the same level. Now these both nodes are present in a different level, it means these both are not siblings. All right. But if we talk about F, G, and H, so these all three nodes are in the present in the same level. Also, they are pointing to the same parent node, that is E. So it means F, G, and H are siblings. Now, the next one is label. A label is a number of parents node corresponding to a given node of a tree. So number of parent node. This is a parent node. This is a parent node. This is a parent node. This is not a parent node, but this is also a part of the label. This is L1. This is L2, and this is L3, and this is L4, right? And these are correspond to its parent node. Now, moving forward to the next component, that is subtree. So subtree of a node is defined as a tree which is a child of a parent node. So we have node A, for which the child node is we have B. Now B uh, is having its own child, that is D and E. So if you look into this graph, it is creating a subtree in the main tree, right? Likewise, E is a child node for parent B, but E itself is having its child, that is F, G, and H. And this is also framing a subtree in the main tree, right? I hope you understand this also. Now, moving next to another component, that is parent. So parent node is nothing but a node which is immediate node to its child node. So we can have multiple parent node, but we can have only single root node, right? Because this is a root node. We can call this node as parent also, and as this is also a parent node because it is having its own child. And this is a parent node, right? Along with this, this is also parent node, and these are the childs. So you can see we have one parent, two, and three. So we can have multiple parent, but we can have only single root node. Now moving to the last component, that is keys. Keys represents a value of node. So as in the tree, we have multiple parent and child node, and each of the node is containing its identification. That identification is nothing but a key. So for the root node, we have identification, that is A, and for left and right, we have uniquely identification by using key, that is B and C. So you can see for the remaining nodes also, each of the node is having its key that represent the name of the particular node, right? So these are the components of tree. Now let's move forward and discuss about binary search tree, as it is a part of tree only. So a binary search tree is a nonlinear data structure that is used to represent the data in a hierarchical form. It can be defined as a collection of objects or entities called as nodes that are linked together to simulate a hierarchy. In a binary search tree, we can have zero node, we can have one node, or we can have two nodes. But there cannot be more than two nodes in a binary search tree. Now let's discuss about the properties of binary search tree. So the value of left node must be smaller than the root node value, and the value of right node must be the greater than the root node value, and the left and right subtree each must also be a binary subtree in the main tree. So let's discuss the representation of binary search tree with the help of example. So here we have a list of integers that we want to represent as a binary search tree. So we'll start from the left hand side towards the right hand side, and the first element which we are going to add in the binary search tree is 50. So this 50 is the key of this node, and as it is a first node, so it will become a root node of the binary search tree. And when we say node, this node will consist of two things. One is the key of the particular node, and other one is the pointer of its childs. So in binary search tree, we can have maximum two childs. That's why we kept here two reference. One is left side reference, another one is right reference of the same instance. So the next element which we are going to add is 35. Before adding 35 into binary search tree, we'll be comparing this 35 with the value of root node, and if it is less than, we'll kept it to the left hand side, else we'll keep it to the right hand side of the root node. Let's see uh, whether it goes to left hand side or right hand side. So 35 is lesser than 50, definitely it will go to the left side of the root node. Now the next element we have 60, so we'll be comparing 60 with the root node first. If it is greater than, it will go to the right hand side, else it will go to the left hand side. So 60 is the right, 60 key is a greater than the root node, which is 50. So definitely it will go to the right hand side of the root node. Now the next we have is 40. So 40 will be comparing first with the root node. If it is, yeah, as it is lesser than, it will come inside left hand of the root node. Then the 40 element will compare with this left hand side node. As it is 35 and 40 is greater than, it will come the left hand side of this 35 node. See this. Now the next element which we are going to add is 70, and 70 we have to compare with the root node first, and it is, as it is greater than the root node, it will go to the right hand side of the root node. Now we have another element in the right hand side, so we'll be comparing with that element. As 60 is lesser than the element 70, so it will again go to the right hand side of the element 60. See this. Now another element which we are going to add is 20. So 20 will be comparing with the root node. I think you are observing that each of the element we started comparing from the root and then if it is landed to the left hand side, so we have to compare the left hand side. If it is landed to the right hand side, we have to compare with the right hand side node. Likewise, now the next element we are adding is 20. So 20 we are comparing, as it is lesser than the root node, so it will land up to the left hand side. Now again 20 will be comparing to the left hand side node, that is 35. Now 20 is again lesser than 35, so it will again land up to the left hand side of this 35 node. See this. Now the next element which we are going to add is 10. 10 is less than the root node value. Definitely it will come inside left uh, side, and then 10 is again lesser than 35, it will again land to the left hand side. Now we'll compare 10 again with the left hand side left hand side value, that is 20. So 10 is again lesser than the 20, it will come to the left hand side. See this. Now the next element we are going to add is 30. 30 is again less than to the root node value, it will come to the left hand side value and compare with the parent of this node. Sorry, it will compare with the 35. So 35 is greater than node 30, it will again come to the left hand side. Now here the left hand side node is smaller than the node which we are going to add, so because uh, the element we are going to add is 30, as it is greater than the left hand side node, so it will landed up in the right hand side, so it will place to the right hand side. Now the next element is 52. So 52 will compare with the root node as it is greater than the root node. So it will go to the left side of the root node. So sorry, right side of the root node. Then we have 60 node here. So we'll compare with the element which we are going to add. So adding the element which I am going to add is lesser than the right hand side value of the node. Then it will go to the left hand side of the right hand side node. So see this. Now there's no anything uh, pending to add. So this is the binary search tree which we have framed with this list of integers, right? And each of these elements is consist of these three values: integer type of data, and node left, which is left is nothing but a reference of the left hand side, and the node right, which is right side of the reference of that particular um, node. Now these are the, I think, components which we already discussed. This root, and these are the parent node, because this child is become parent because this parent is having its own childs, and these are the leaf nodes, because this is leaf node, this is leaf node, this is leaf node, because there is no anything next to these nodes, anything in the sense there is no any further child next to these nodes. So uh, not only that, but this is also a leaf node, this is also a leaf node, and this is also a leaf node, this is also a leaf node, this is also a leaf node. If you look into this structure, right, this child is framing a tree because this child is having its own child, and because of this child, this 20 node will become parent, right? So this this one is framing a subtree as mentioned here. Along with that, this is also framing a subtree, right? And this is also framing a subtree. So as we discuss it while discussing about the component of tree, um, see this these two nodes are siblings. How these are siblings? Because these are landing in first, second, third. These are landing in the third level, and both are pointing to the same parent, same node, and because of that, these both nodes become siblings, right? So these are the representation of the binary search tree with the help of integers, list of integers. Now, let's discuss the traversal of binary search tree. So the first type of traversal we have pre-order traversal. So as mentioned by its name, as it is pre means we have to traverse root node first, right? So in pre-order traversal, we will be traversing root node first, and then left node, and then right node. So in case of in order traversal, as it is clear by its name that it is in order, means root node will be traversed in the center of left and right. So in this traversal, we have to traverse left node first, and then root node second, and right node at the last. So in post order traversal, as it is clear by its name that root node will be traversed at the last. So how we are going to traverse here? We will be traversing left node first, and then right node second, and then root node at the last. So these are the type of traversal in the binary search tree. So I hope you found this video is very useful for you. And that's it from this video, guys. And stay tuned for another videos of the binary search tree. Thank you so much for watching this video.